Well, it means it's safe.
It smells like perfume. It's my beef stick. Yeah, natural aging. The thought that lives in my head right now. That's literally. You can never be too fantastic. And I can hear it. They'll die. It's really low to the floor. You're not invited to the house.
Okay, well, happy Friday. Yay. I understand I'm standing between you and your weekend, but hopefully I'm not.
Not today.
Okay. All right. So let's see. I want to finish the HPLC lecture for sure and see if I'll have a little bit time to start a new segment, which is spectroscopy, but we'll see how it goes. All right. Let's just, like usual, just do a bit of a recap. Can you explain to me how temperature can impact resolution in your own words? What happens if we increase a little bit the temperature? What happens, Ali? Yes.
Increasing the temperature, it decreases the viscosity of the solution.
Yes.
So it'll decrease retention time.
Yes.
Faster.
Yes, this is all correct. In addition, it will enhance resolution of compounds because you will reach equilibrium faster. Because of thermodynamics, you will have your components, transitioning between stationary phase and mobile phase to reach an equilibrium faster. So you will have really nice, sharp, well-separated peaks. Of course, you don't want to exceed the temperature so that movement is too fast for equilibrium and also degrade the column. So we always try to figure out this optimum temperature where we reduce the viscosity of the mobile phase, have a little bit of thermodynamics going, where movement is faster, equilibrium is faster. That means you reach equilibrium faster, you get better resolution, and as Ali said, shorten the analysis time because retention time will be short. All right, all of that. Okay. Now, what about flow rate? What happens if we increase the flow rate? You know how you have like 1 mil per minute. What happens if we go to 1.2 mil per minute? Yes. Yes, faster elution and also faster reaching equilibrium faster. Same with the temperature, but a different mechanism. You have better, quicker movement, but with the flow rate, you want to be careful not to be very, very fast, then you don't reach equilibrium. And then that would be bad for resolution. That's why if you remember the relationship between height equivalent of a theoretical plate graph and the rate, so x-axis was the rate, y-axis was the height equivalent of theoretical plate. So you see that it goes down when you increase the rate and then it slowly goes back up. So you don't want to be too fast. Okay. So how does the packing and thickness of the stationary phase impact resolution? So if it was a thin stationary phase versus really thick stationary phase, which one will have better resolution? Yes?
The thicker the stationary phase is, the better resolution.
Okay, so you're not wrong in a sense that if you have more stationary phase, you have more capacity on the column, that's true. But if you have thinner stationary phase, you have that C factor in the equation. If you remember the mass transfer factor will be small because you don't have a lot of like diffusion into the stationary phase and getting delayed and lost and diffusing down versus going in and out. The thinner the stationary phase, also the faster the equilibrium. But so better resolution. But sometimes you need to think, you're not wrong here, Golden, because you need to think, do I want capacity or do I want better resolution? Sometimes your peaks are very well separated. You don't have to worry about it because they're very structurally different, and you need to collect that fraction for another analysis. So you care for capacity. Then thicker would be better. Okay, so yeah, so there are different perspectives. Yes, Lizzie.
Some of the difference between packing and thickness, because like a more densely packed column would have greater resolution, right?
Right. Yeah, so
But
that's the
so-
difference. Densely packed, meaning your particles have not a lot of open space between them.
So would that inherently make a more thin column?
No, not necessarily. You can have a packed column with a lot of stationary phase, but it's well packed. The particles, in a sense, there's not a lot of void between the particles. But each particle has pores, remember? So that you have to think about two things, the pore size and the size of the particle and how well packed. So there's three different things, okay? So when you have your particles, you want to pack them as tightly as possible so you don't have empty space in between. So that's good packing. But also, every particle has pore size. So which pores in them? Naturally, they will have pores. So you don't want your sample solute to go into this pore and get kind of detained and diffuse because that will impact the solution. And then if you have a thin layer, let's think of a capillary tube, and you have a thin layer of your stationary phase, there's not a lot of room to go in and get lost. So they will go in and out very quickly. But if it's not well packed, then we defy the purpose, because here it's made up of particles too, right? Your stationary phase is made up of particles. If they're not well packed, that will defy also the resolution. Yes.
So you don't want it to be thick?
So you want it to be well packed, for sure. That has nothing to do with thick or thin. Small particle size, well packed, not a lot of void volume.
Small particle size.
Small particle size, well packed, and no, as little of empty space as possible. We cannot, but all particles have pore size. So there's particle size and pore size. That's part. This is a particle size, and then they have pores in your particle. Yeah, so that's different from the particle size. Now, as I was saying to Golden, though, you sometimes, if you have already good resolution, your compounds separate really well, and then you need to collect at the end of the chromatography, you need to collect and go do a mass or NMR or whatever. So you need capacity. You need to inject more of the sample, so you have less how many times you're going to inject and collect. Then you need a thick stationary phase because you already have good resolution. And you need more capacity, you can inject more because you have more functional groups that can interact with your compound. But if you're really doing analytical HPLC and you're just, or GC, and you just want to detect, identify, and quantitate, and then your peaks, your compounds are very close to each other, you really want resolution more than quantity, then you go with thin stationary phase so that you can get good resolution and you don't care about capacity as much. Does that make sense to you?
Yeah.
All right, very good. So this ties into the next question. What's the advantage of a narrow diameter? With a narrow diameter, you have less stationary phase, so better resolution. Okay, you reach equilibrium faster, your mass transfer is low, So basically you have better resolution. Narrower column is equivalent to less stationary phase, basically. Narrower and longer. So the longer your column is, the better you have more theoretical plates, more room to interact and separate. And the narrower it is, you have less packing material for the compound to spend on the column. So we talked about HPLC being more beneficial or advantageous than low pressure because you have better resolution, it's faster, and the column usually can last. You don't have to pack and repack and repack. So yeah, talked about that. And now you are pros in gradient versus isocratic, right? What's gradient illusion? Yes. Yes. During your analysis time, you are increasing the strength of the mobile phase. You're changing its concentration or its composition over time. So it's not always in one direction, remember. It's not always increasing the organic phase or organic solvent. Sometimes you increase the organic solvent, like in normal phase. Sometimes you increase the water concentration. Sorry, reverse phase, you increase the organic solvent. And sometimes in normal phase, you increase the water concentration. So it really depends on the mode of your chromatography, in which direction you change the composition of your mobile phase during the analysis. So what is the function of a guard column? By its name, what is it doing? Is guarding the column from what, Lukman? You're looking at me smiling. Why are we guarding the column from? Yeah, so exactly, we are protecting the column from impurities that would just stick on the column and block functional groups and just make the column not efficient. Do we have guard column in GC? What do we do in GC? We cut the column. We cut the first component part of the column after so many runs because that first part of the column acts as a guard. In HPLC, do not cut my column. It doesn't get cut. So yeah. So we have a guard column, small. Okay. How many solvents and pumps can one use in HPLC? Was that many? Yeah, it's a good answer. We can use 1, 2, 3, 4. We don't necessarily, it's not usual to see 4 pumps, but it's usual to see 4 mobile phases with 1 pump or 2 pumps. So it depends on the mixing. If you have 1 pump and 4 reservoir, then the mixing is low pressure before it goes into the pump. If you have, like we have in our lab, 2 pumps, 2 reservoirs, that means each pump is pumping 1 solvent or 1 mobile phase and then mixing them under pressure before they go on to the injection port and down to the column. So yeah, you can have, I've seen maximum of 4 is what I've seen. And as low as 1 if we are just having isocratic illusion. Okay. Very good. Any question on anything? All right. So there are different types of columns. So we have something called microbore and micro columns. So microbore, it has to do with the diameter. So the diameter is between 0.5 to 2.5 millimeter. Now, anything smaller is a microcolumn or a capillary column. So both microbore and microcolumns are packed, meaning the column is fully packed. There is nothing hollow inside. Capillary is hollow inside and has a thin stationary phase around the interior of it. Okay. So capillary usually have similar diameter to microcolumns. The difference between a microcolumn and a capillary is a microcolumn is packed, completely packed from top to bottom, where the capillary is a thin layer on the internal and it's hollow from in the middle. So in HPLC, these columns usually are packed with really fine particles, so small particle size packed under pressure, so very, very small void volume. And in UPLC, which is ultra high performance, usually we use the small columns and most often capillary column, because these would withstand higher pressures. And with those small columns, we get better resolution and very short analysis time. We're talking 5 to 10 minutes. So in this case, we don't necessarily collect fractions after a UPLC column. They're very, very small, very, very small capacity, but really good resolution and short time for analysis. So they're advantageous when we really want to do analytical work, detection, identification, quantification, have good separation, and we don't care for collecting. So we don't care as much for capacity. Okay. Okay. So let's see. From what I've been chatting about, can you answer this question? Oh, man. No, no brave guessing.
G. Will be look.
Yeah, when in doubt, right? Yes, yes, yes. So let's explain that. So, like I said, smaller diameter column, so less stationary phase, so you get better resolution because you have less, the C factor in your equation is low, mass transferred. It doesn't, compounds don't get really lost and interact for a long time on the column. There's not a lot of stationary phase. And when you have this very small diameter and a little less stationary phase, your peak will be higher in height. Not necessarily larger area, but will be sharper peak. Better resolution, sharper peak. So your peaks are really sharp. You hardly see something like an area, but compared to something look like this. So these two might have the same area, but this is really sharp. You're enhancing the sensitivity of detection, because now you can detect it and it is moving down the column as a really, really sharp band. So it's not diffusing. So it's staying sharp, highly concentrated, then you get really sharp peak. And whereas here, every fraction of a second, a little bit is coming out because it's spreading. A little bit is coming out and there's not much in there. So your sensitivity is way low. It becomes close to noise if you have low concentration. So definitely higher height, better enhanced detection because you have better sensitivity, better threshold of detection. And yes, reduced equilibrium time, like we talked, less stationary phase, you reach equilibrium faster. Okay. So the packing material of the HPLC has to be durable because it's packed under pressure and it has to withstand the equipment pressure. There's always pressure generated in high performance liquid chromatography. So, and the packing material can be a support, like non-reactive, and you have a thin layer of reactive stationary phase, or it can be all of it the stationary phase. Like I said, well-defined, small particle size, very good ability to pack with low void volume, and can withstand mechanical stress due to high pressure. And you don't want it to dissolve in your mobile phase. So you want chemical stability rather than chipping away your functional group with every run. Or having it, interact covalently with the components and then it degrades over time. So, and then the pore diameter, the smaller the pore diameter, the better, okay? Because then you will have less just diffusion, a non-specific diffusion in your column, which will reduce resolution. All right. Okay, so it's kind of like all the same theme. We all care for resolution, particle size, durability, pore size. Yeah, kind of like same theme. All right, so the packing material, most commonly it is silica bonded to something. Either bonded like a C18, like we used in the lab for reverse phase chromatography for caffeine, or it can be bonded to a charged acid or charged base, so that's anion exchange or cation exchange. So then you will have your interaction with your components. Sometimes you have an inert core and a thin layer of stationary phase. That's basically when you care for resolution and you don't care for capacity. And the inner core is non-reactive, non-porous, and then the thin layer is your stationary phase that interacts with your components. And then two other types of stationary phase are polymer, either micropores or macropore and micropore. So either a polymer that is loosely linked for large molecules, or a polymer that is highly linked with small pores for small molecules. And this is common for size exclusion and anion exchange polymers. All right. You already saw an oven in the lab where we store our column. And like I said, temperature is important. And sometimes you want to just run at room temperature. You don't really want to increase the temperature. But why do we have an oven still? If you don't care, you want to run at 25 C, room temperature. But we still put it in an oven. Yes, Mary. Huh?
Constant temperature.
Constant temperature, because think of our poor AC system. So either you're very cold in this lab or you're very hot. Depending on the season and whether it's heating or cooling, we never have constant temperature, room temperature. And if temperature fluctuates, your retention time fluctuates, your resolution fluctuates, you're running the standards, and then your unknown is coming at a different retention time, it's a mess. So it's always better to have your columns stored in an oven and at a constant temperature. And we raise it. I think the example, we have 40 or 38 degrees we ran caffeine at. You remember? 37. Yeah, so we do some trials at the beginning to kind of find the best temperature, not too hot, not too low, to have that enhancement in retention time, resolution, and we don't lose on equilibrium. All right. I'm going to move into detectors. Any questions so far? Okay. So the most common detectors in HPLC is based on absorption of light. So we have absorption of light. We have a very common one, cheaper than others, which is the one that you fix at a constant lambda or wavelength. And this is called variable wavelength detector. Well, I did say constant, but what they mean by variable wavelength detector is you can select the wavelength and set it. So it's not only at one wavelength. The spectrophotometer would work at multiple wavelengths, but at the beginning of the analysis, you set it for caffeine 282, let's say, lambda max. You set it, and then you run. And then if you're running isoflavones, you set it at 254 nanometer. So you can select, that's what it means with very variable wavelength detector. Now the other components, and Reza talked to you about that for the photodiode array, is we have lamps that are the sources of light. And UV vis, meaning you can run at absorption in the visible range or absorption at ultraviolet range, which is 200 to 400 is ultraviolet, and then 400 to 800 is the visible. But you need two different types of lamps that will give you the light in that range. Deuterium, usually it's in the UV range, and tungsten gives you light in the visible range. Some detectors have both lamps, so you can switch them both on depending on the analysis, or switch one on and turn the other off if you care for one or the other spectrum. So the benefit of variable wavelength detector, well, you can select your wavelength, and usually if you know your lambda max, you select it from the beginning, and this will allow you to quantitate at maximum sensitivity, because lambda max is the wavelength at which you have maximum absorbance. Okay, and by doing so, you follow Beer's law. It's coming. It's gonna come next week. Beer's law. Anybody remembers what Beer's law is? No, it's in the past. It's way in the past. Anybody remember the past? So sad. Okay, let's try to remember the past. I just want to, because we'll talk about it more next week, but do you remember this equation? Yeah, equals, so absorption equal A, B, C. Do you remember that? Does it ring a bell? All right. So absorption, this is absorptivity, concentration, and then the length. So it is the equation that gives you linear relationship between absorption and concentration. So you follow this, you meet Beer's law when you're measuring absorption at a singular wavelength. So that's kind of the benefit. You can quantitate at a singular wavelength and you meet Beer's law. Okay, so sometimes you it depends on the detector that you have. You can monitor at 2 channels. You can monitor at 2 different wavelengths. So this will be a little bit more expensive, advanced. Sometimes you can switch the channel in the middle of the run. Next week, I'll talk about a monochromator and the role of monochromator. When light comes, you select one wavelength before it goes onto your sample for absorption. And that's what happened in variable wavelength detector. You have a monochromator, a unit that selects a singular wavelength. Okay, we'll talk more about that, so don't worry about it now. Yeah, and sometimes you can switch the monochromator in the middle of run. You know that you have 2 components. One has a lambda max at 254 and one has a lambda max at 280. So if you know when they're gonna come out, you can program the first 10 minutes, let's monitor at 254. The next 10 minutes, let's monitor at 280. All right, now photodiode array detector is the workhorse in HPLC because it helps us detect, identify, and also quantitate. So it's a very powerful, I mean, not the best identification tool, obviously, but it's much better than variable wavelength detector. And that's what you saw in the lab. Because what it allows you to do, to get is three-dimensional data. We talked about it last time a bit. Three-dimensional data, meaning you get two kind of outputs. One, it shows you the one-dimensional or two-dimensional, where you just see a heat coming out. Here's time, here's absorption. And then at every fraction of a second, 0.01 second, you get another window that shows you absorption over lambda. So nanometer. So it gives you this kind of spectrum. Absorbance over a wide range of lambda. It's like your fingerprint for the model. So that this allows fingerprint to a certain extent. That gives you a unique identity. So sometimes when you're just looking at one peak, you might have two compounds coeluting and you don't see them. You just see one peak, but they both are very structurally similar. They're coming out at the same time. You don't see, you just see one peak. But if you look at the spectra, you'll see different spectra for two different compounds. And I think Andresa showed you that in lab, right, Andresa? A little bit. Okay. So what happens in photodiode array detector, you don't have a monochromator. You don't select a wavelength. All the light hit your sample, and your sample absorbs at all of possible lambdas, and then the remaining light goes in onto a kind of a tray. It's an array of photodiodes. And each wavelength gets converted from being a light to an electrical signal and gives you the spectrum. It's a very, very cool instrument to have. And this is what it differentiates, exactly what I said here. If you have two compounds, you're looking at pyrene and an impurity. Using just a single dimensional UV with just looking at time versus absorption, you will just see one peak, but underneath it or within it, there's another compound, but you don't really visually see that. But when you look at the PDA, you see two different spectra. You'd say, one is pyrene, the other is an impurity. So let me work on resolution so that I can get the exact area under the curve for what I'm trying to quantitate, which is pyrene in this case. So that's the power of a PDA. Okay, so the other also common detector is a fluorescence detector. And next week, when we talk about spectroscopy, we know that sometimes we will measure absorption. Sometimes we will measure emission of light, which is the fluorescence. You know, every molecule or atom goes into the excited state. I will remind you of this light physics next week. You go into excited state, but it doesn't stay there. It goes back to ground state. As it goes back to ground state, it emits light. Some molecules and atoms emit enough or fluoresce enough for detection. So it can be detected. And sometimes detecting fluorescence add more sensitivity, enhances the threshold. Like vitamins, for example, we measure fluorescence, in some cases, more than absorption. Refractive index. So refractive index is based on change in concentration of the mobile phase, dissolved analytes of interest. It changed the refractive index. So it's used very commonly in carbohydrate analysis. And in that case, you only use isocratic elution, because if you change the concentration of the mobile phase over time, it will change the refractive index. And you don't want that. You only want the refractive index to change proportionally to the concentration of the solute. Okay. Another one that some people confuse PAD versus PDA, they're very different, but they have the same letters. Pulse amperometric detector, PAD, is different than photodiode array detector, PDA. So try not to confuse them. And these detectors are usually used with molecules or compounds that oxidize or get reduced, and that will cause a change in current. And then you would measure the change in current. Or sometimes that when charged components are in the eluent, you can measure conductivity because the ions will change conductivity. So in either case, whether we're looking at oxidation, reduction, and change in current, or change in conductivity, this can be done with electrochemical detector, known most commonly as pulsed amperometric detector. And it's mostly used for compounds that can be oxidized or reduced or carry charge, that kind of thing. Light scattering detector is known as a universal detector. You know, like in GC, thermal conductivity detector is a universal detector. In HPLC, light scattering detector is a universal detector, meaning it works with anything. The compounds don't have to absorb light. You can run with a gradient. They don't have to fluoresce. They don't necessarily need to be charged. What does it do? So your compounds are traveling with the mobile phase. When they reach the detector, there's heat that will evaporate the mobile phase, and your compounds will settle on a source of light, and they will scatter the light. And that scattering is proportional to the concentration of your solutes. It's very commonly used with size exclusion chromatography, and the detector specifically is multi-angle light scattering detector, MALS. You will hear it if you might encounter it in future life. It's multi-angle light scattering detector, very sensitive universal detector that is commonly used with size exclusion. And then, of course, there is linking your liquid chromatography with mass spectrometry, which is highly sensitive, and you can get structure elucidation, you get molecular weight, you can get something called M by Z, molecular weight by charge, a lot of information. And Gary will talk about MS later. Chemical reactions. Sometimes we're analyzing compounds that are not naturally chromophores, but you have a UV detection, or you have an absorption spectroscopy or a fluorescence spectroscopy. So, but your molecules or compounds, they do not absorb light. So you induce a chemical reaction. Let's say amino acid, you reacted with an OPA reagent, or you reacted with anhydride, then it forms a compound that actually absorbs light. All right. Questions? All right. So in that chapter, in your book, chapter 13, there is a summary table that gives you an example of different analytes that can be analyzed by HPLC. And then it gives you the separation mode, the method of detection, and then which chapter and section they're going to be covered. So in future chapters, we're going to have a chapter on carbohydrate analysis. We're going to talk about vitamins, protein, pesticides, mycotoxin, antibiotics, and other compounds. And then we will need to know the principle of chromatography, because we will, like, if you get a question in the exam, I'm gonna tell you, if you wanna analyze this component, what mode of HPLC separation would you use? Give me an example. This is a good study thing, basically. All right. So I'm gonna go brief over this because there will be a lot of application later on in chapters, and you already know what normal phase is, right? Normal phase, your stationary phase is polar, relatively polar, your mobile phase is relatively nonpolar. The difference between normal phase and hydrophilic interaction liquid chromatography, hydrophilic liquid interaction chromatography. I'm just looking at the abbreviation. So it is also normal phase, but the only difference is the mobile phase is miscible with water. So you can use acetonitrile, for example, so that you can link mass spectrometry as a detector. That's only the difference. And I give you an example of what it can be, each can be used for. We all know now reverse phase is the reverse of nonpolar. So your normal. The stationary phase is nonpolar, your mobile phase is polar. And then there are a list of different compounds that can be analyzed, and caffeine is an example that you did in the lab. Ion pair reversed phase. You can use reverse phase for charged molecules. Just add ions to your mobile phase to kind of neutralize the charge and allow relatively nonpolar interactions to occur. That's what ion pair, meaning just putting more ions in your mobile phase to neutralize the charges on compounds. And these are just FYI example using different phases of normal and reversed. Okay, ion exchange, we talked about it, and these are a list of components that could carry charge. Size exclusion, I made a correction. I should have made that correction before putting the slides up. Originally, a few years ago, it was not very commonly used in high performance, but now we use it quite a bit actually for molecular weight determination, whether for carbohydrates or proteins. It's really used for a calculation of molecular weights. And then affinity chromatography, we talked about it. And then these are different examples. This is FYI, the shapes of size exclusion. This is actually very bad. In a sense, you don't have really sharp peaks, but this is from preparatory size exclusion. So it's not really analytical. Your low pressure columns, big columns, and you get really wide peaks because you don't have very good resolution. This is a reminder for me, I should put chromatograms for HPLC size exclusion that we get for proteins, actually better shaped peaks. All right, now for the last few 4, 5, 6 minutes, I want to do this exercise with you. It might show up on a quiz. I don't remember if it was in last year's quiz or this year it's gonna be on the quiz. Maybe, who knows? But let's solve it together. So you can take out a piece of paper for a +2. How about that? And then make sure before you give me that paper, take a picture of it so you'll have the answer. All right. So there are questions on the next slide, but let me give you an introduction of what you're looking at, and I'm sure you you showed them isoflavones in the lab, right? Yeah. Okay. So in soy, we have phytochemicals called isoflavone. They have antioxidant properties, physiological contributions, so they're important to kind of analyze. And this is a standard mixture of all possible isoflavones that could be found in soy. Okay. So we have, I think the slide shows 11 of the 12 isoflavones. We didn't have one standard. Is that 11 or 12? 1, 2. No, 12, right? Am I making this up? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, all of them. Okay, so 12. So these are the standards mix. And what this is showing you here is the mobile phase starts at 17% acetonitrile, which means 83% water and 17% organic. So 83 water and 17 acetonitrile organic. And this is the program of time. It's a 60 minutes run. And this is the program of the gradient elution. So you start at 17, over 25 minutes, it increases 25. We have an isocratic between 25 and 30 minutes. Then from 30 minutes to 40, it goes from 25% to 30%, then stays constant for 10 minutes, and then comes down in the last few minutes to 17%. We always start and end and allow equilibrium time before the next injection. So if we start at 17, we have to end at 17 and keep it for few minutes to equilibrate the system so that everywhere in the system it's 17% acetonitrile, then we're ready for our next injection. All right, so now that I explained this to you, let's answer. Is this normal or reverse phase chromatography? Yes, how did you find that out?
83% of water.
Yes, very good, well done. Yes, when we're starting with more water, so it's more polar mobile phase, then your stationary phase is the opposite. So reverse phase, you have non-polar stationary phase and polar starting mobile phase. So yes, it's reverse phase chromatography. Which of these isoflavones, the first or the last, is the most polar? The first, thank you. I was gonna call your name out. You answered before I did. Telepathy. You knew that I was gonna say golden. Yes, because the least polar will interact the most with your non-polar stationary phase. And then the most polar would like to come out with water. So it doesn't want to interact. So the most polar will come out first. Very good, very good. Okay, so how would you change the mobile phase so genistein would elute sooner without changing the relative positions of the other compound? So genistein is the last one. So what would you do differently in your program to let this come out, let's say, instead of 50 minutes, 40 minutes, 38 minutes, without changing the positions of the other 11? Yes.
Would you, after the, like 38-minute mark or something, like when you're at the 30%, would you just raise it past 30% acetonitrile? Like what if?
Yes, absolutely. Look, you have about 10 minutes where there's nothing coming out. So after the time of this last 11th isoflavones comes out, so instead of just keeping it at 30%, let's increase it to 40%, for example. This will make that least polar isoflavone like the mobile phase better. Now there's more organic solvent, so I can come out sooner. Very good, very good. So let's say you kept an isocratic elution at 17%. What would happen? You didn't change anything. You just kept 17% from beginning to end. What would happen? Devin, I want to see if you will be able to answer this. I know you know, but so what happens if you do not increase the organic phase? What happens to all of the compounds? They will come out, will not come out. What was that? Will not come out. Yeah, they will come out eventually, but very late. Because now you're not increasing the strength of the mobile phase. Thank you. Yeah, good. So you are increasing the, yes.
What time it would take?
No, you just sit there and wait. It's just gonna take forever. And then not only that, you might lose the resolution because these here are very close to each other, and then your peak will widen because it will diffuse inside of the column and then they will overlap. So you will cause all sorts of havoc. You lose the separation at very key places because the peaks will widen, and then your retention time will be like much longer, and you will sit overnight and you still don't get all your compounds out. So it's not a good thing. You don't want to do that. All right, last, what would happen if you keep an isocratic solution at 30%? William, you want to tell me? Yes, thank you. Yes, so they're all going to come out now, all at once, and we lose definitely the separation between those that were close to each other. So maybe we will get one peak here, one here, one here, and one here. So maybe you get 4 peaks instead of 11, and they're all going to be crowding each other. Okay, so also not so good idea. All right, very good. In the last, well, I don't have a minute, but very quickly, I want to demonstrate without too much detail that we use HPLC in tandem. We can have 2D, 3D HPLC. So we can fractionate with one mode of separation, take a fraction and separate it again with another mode 3 times until you get a pure component. So the example here was antioxidant. We used anion exchange and we separated. We took the one that had the highest antioxidant and separated by size exclusion. Then we took the one that had the highest antioxidant activity and separated by reverse phase. And then we did LC as MS tandem to identify the structure of that purified component. Because remember, some components, in this case peptides, have similar molecular weight, similar charge. So you keep using different characteristics to get to a pure peptide and then characterize it structurally by ends. So that was the kind of the message here. All right. Thank you. Have a great weekend.
Might actually don't. So much. Actually.